Good evening, everybody, and warm welcome to you all from both sides of the Atlantic. I noticed this evening, you're all very welcome. And also those of you joining us at some point in the future on our YouTube channel, you're also very welcome. Next month, we've got Professor Thompson from Sheffield University, and he will be talking to us about cosmic radiation and muon tomography. So that's something a little bit different, just on the edge of radio astronomy. However, tonight, I'm really pleased to introduce Professor Carole Mundell, hardcore radio astronomer, I think. And she's an extragalactic observer from the University of Bath. So we've also, a little later, got Wolfgang joining us again to update us on his latest results, and that will complement, I'm sure, Carole's presentation. And then at towards the end of the evening, we've got Whit Reeve is going to share some results, because the sun, as many of you will have noticed in your own observing, has been incredibly active over the last few days. So without any more waffling from me, over to you, Carole.
Well, thank you. Just let me share my screen here and get set up. Give me 1 minute. So it's a real pleasure to join you all tonight, and thanks so much for the invitation. As you say, I am a hardcore radio astronomer, so I did my PhD many years ago at Jodrell Bank Observatory, and I used the E-Merlin array, it was Merlin in those days, and also the very large array in New Mexico to study atomic hydrogen in distant galaxies, and to use the gas dynamics to actually weigh the host galaxies and to try to understand how supermassive black holes get fed at the heart of these galaxies. And tonight I'm actually going to broaden across the electromagnetic spectrum, because through my career, I've moved sort of up in energy. I still use the radio, and in fact, we're going back now and using the radio in very novel ways, which I'm happy to talk about in the questions. I actually haven't put in the presentation here, but I'll put that plug in for your audience if people want to come and ask me what about the radio for gamma ray bursts. And tonight, what I thought I'd like to do is actually take you on, let me see if I can move on. That's it. Take you on a whirlwind tour of the universe, really. And I want to put the gamma ray bursts into context. And it's really exciting that Wolfgang will share his results on the FRBs after me, because I think the story of cosmic discoveries is actually a pretty standard one. We find something at some wavelength in the universe. If it's not in the optical or the visible light, we don't know how far away it is. And you'll see this as I develop the gamma ray burst story, how similar this is to the fast radio bursts. But of course, the fast radio bursts are even more technically challenging than the gamma ray bursts. And so, of course, we start fairly close to home. As you mentioned, Paul, you mentioned the sun. It has been pretty active right now, and you'll all have been seeing that in your radio observations. And this, of course, is not a visible light picture, but not a broadband picture. You can see here the sun in the top left-hand corner. And the reason I'm showing this, apart from the fact that the sun's really important for us and it's nearby, is really because I want you to think throughout all of this about the magnetic fields. And again, some analogies between the physics that we think we understand, or we can study in great detail in the sun in terms of reconnections, and how the magnetic fields drive the solar wind, and what we're starting to try to do in gamma ray bursts in my research group. Of course, if we go a little bit further out, we then have the Pleiades star cluster, which would have been very bright and young when dinosaurs were roaming the Earth. And I love to have that connection between cosmic timescales and planetary timescales, because when we get to gamma ray bursts, we're really talking about fast human timescales. If we draw out a little bit further, and if we were able to fly in a spacecraft above our own Milky Way-like galaxy, we would see a galaxy very much like the one here in the right middle of the screen. So our Milky Way galaxy is a spiral galaxy. It has dust, it has gas, it has stars, and it has about 100 to 200 billion stars in the Milky Way. And then if we zoom out again and we look at the universe, we think there are about 100 to 200 billion galaxies in the universe. And I always say to my students, so you can do the math, you can figure out how many planets there are, and you can then figure out what the chances that there's intelligent life in the universe. And indeed, sometimes you can wonder whether there's intelligent life on the Earth, but I think that's a philosophical rather than a scientific point. And if we zoom into a patch of the sky, this is actually one of the, I think, if not the most deep optical images ever taken of the sky. So it's called the Hubble Deep Field. And the Hubble Space Telescope stared at a patch of the sky for many, many weeks, gathering all the light. And it did it in several colors, and then combined these images to make this nice, this color photograph. And what what's, I think, fantastic about astronomy is it's visually very beautiful. Of course, you could put this on the front page of your newspaper, you could print it, you could stick it on your wall, and it would be very beautiful to look at. But we've got a huge amount of physics encoded in the light here. And again, that's really a theme throughout this talk and through probably many of the talks that you have here. How do we decode physics of distant objects, complex objects that we don't necessarily know how and why they're behaving, by just decoding the information that's trapped in the light that we detect with our telescopes. And of course, here on the left-hand side, you can see a red and dead galaxy. In the middle, you can see new blue star-forming regions. And down in the bottom, in the middle, you can see the sort of pink-orange galaxies. And they're actually galaxies that are getting close to one another and are being ripped apart by the forces of gravity. And of course, we tend to think in the universe of forces that gravity is a weak long-range force, but when you're out at cosmic distances, you can see that it's actually a very powerful and disruptive influence. And of course, it forms much of the structure and the behavior of the structures and the gravitational behaviors that we see in the universe. And so already we can see there's a huge amount of physics encoded in this pretty picture. And in fact, I could tell you what atomic transitions are producing the different colors. We could do the chemistry of the galaxies. We could actually measure how the spectral lines are moving from rest wavelength. So if we have these atoms in our lab, we know exactly what wavelength they should emit light at. But of course, at these distances, the universe itself is expanding. So we can use the shift in the spectral line through the Doppler effect to measure how quickly the universe is expanding. And also, as I said, as I started my PhD in hydrogen, you can do this in other wavelengths as well. You can actually measure how these galaxies are rotating, how the gas is moving, and weigh the galaxies. And of course, this then opens up whole new areas in terms of dark matter, dark energy, and big open questions that we still have in cosmology and galaxy formation and evolution. So lots of physics, lots of lab-based physics being used out in the universe and vice versa. But of course, we're not the first to ever look at the sky. I'm sure we won't be the last. Oh, I hope not. Anyway, that's a separate conversation again about man-made satellites. And this picture for me, I think it just epitomizes the human interest in the environment around us and what the night sky means to us. And this is a cave in Lascaux that was discovered in the 1930s. You can actually go visit there. You can't see the original now because it's all climate controlled, but they've made an exact mock-up so you can walk through the caves. And the artists of the day, or the scientists of the day, however you want to call it, these incredible people were actually painting on 3D prominences. So this bull is actually painted on a bulge in the rock. It looks incredibly lifelike. I mean, you go there, what strikes you is the nature and the wildlife. Your antelopes leaping across the caves, and you could imagine this would be your Saturday night movie. These maybe would have been the elite of their society, and you can imagine how hard it was to lie on your back, painting these things on the cave. And maybe you can imagine that, with a tallow candle, if you lit the cave pitch dark, you would then see these antelopes come to life and be animated across the cave walls. And scientists who've looked at these have really remarked on the powers of observation of these people who painted these, that the antelope's movements are actually anatomically correct. They're actually leaping properly. They've the real powers of observation. But it was a few years before a German archaeoastronomer just figured out that this was not just a painting of a bull on the wall, but it's actually a representation of Taurus, the constellation. And just above the back of the bull, you can see the Pleiades star cluster. So I love to think that image that I showed you at the beginning that we took with a telescope, a CCD detector and a really deep image, these ancient people were looking at the night sky and picking out the same patterns that we pick out today. And then in the bottom left-hand corner, you see a string of 4 dark spots. And there's been some speculation that might be the belt of Orion. But actually, if you look at Orion, there are only 3 bright stars. And so I kind of like the idea that this might have been the path of one of our solar system planets passing across the night sky relative to the fixed background of stars over the course of a month or so. And so maybe these ancient scientists were actually mapping our planets moving in the solar system. So I would argue that time domain astronomy, which is what I and my group research in, began over 15,000 years ago. So I have a nice connection back in history. And of course, how things move on the sky in the dynamic universe has been a story really through astronomy. And I've picked out these sort of 4 seminal names, not all by any means, but Copernicus really was pretty heretical in his day because he put the sun at the center of the cosmology of the day, and that was quite a revolutionary idea. Galileo came along a little bit later, and I think of Galileo really as an early adopter of technology. So the telescope was not invented by Galileo, but he was one of the very first to use the telescope, and he developed telescopes, obviously, really quite dramatically throughout his career. And he pointed his telescope famously at Jupiter and commented that he saw moons orbiting around another world. He says he could not deny his eyes. And of course, that got him into trouble because the church's teachings were that the Earth was at the center of the then universe. And he said, that's clearly not true, because I can see moons orbiting around another world. And again, I think of that almost as the birth of evidence-based science. So he had the experimental evidence, and it didn't matter what the theory said or what the church's teaching said. The experimental data told him something different, and therefore he had to move scientific thinking on. Kepler came along a little bit later, and apocryphal story has it that he went to the widow of the gentleman astronomer Tycho Brahe, who had been gathering observations of the night sky with his own telescopes for many, many years, and mapping out the positions of the planets on the sky, writing down the position and the date. And he had reams of data, and he'd spent his life obsessively looking for patterns in these data and never actually identifying any of the empirical relations. Kepler was a young, enterprising, ambitious young man. And again, for me, this is the birth of data-driven science. We talk about the era of big data, but in those days this would have been the era of big data too. And he apparently took the data from this grieving widow. You don't want this mess all over your house, I'll look after it for you, and putting words in his mouth. I don't know what the actual conversation was at the time. And he then spent his career looking through this amazingly rich data set to try to find some patterns and relations. And of course he discovered the empirical laws of planetary motion, which for the day would have been incredibly revolutionary, because not only were these empirical relations that explained the data he was actually able for the first time to predict what would happen tomorrow and the day after. So the predictive power of science was really then born in Kepler's hands, and it must have seemed like magic. He could tell you where the planet would be tomorrow night, and he would be right. And so that for me really is the birth of empirical science. So you have an empirical relation, you have a testable prediction, you can go and make the measurement and confirm that actually that prediction is correct. But of course he didn't understand the underlying physics. Why were these relations such that they were? Why was he able to predict the future with them? And it wasn't until Isaac Newton came along and discovered the universal law of mechanics and gravitation, invented calculus, that we really understood that it was the attractive force of gravity keeping the planets and their motions around the sun, which of course was the center of the then universe. So I think this is an incredible story of observational astronomy, looking at the night sky, studying the world around us and seeing how it changes with time, that helped us to discover the laws of physics that underpin much of our modern life today. And then, of course, coming forward in time, again, advancing these laws, it was really the work of the eminent mathematician Emmy Noether, working with David Hilbert, who helped Albert Einstein to really put the finishing touches to his equations, the general theory of relativity, which really updated and gave us a broader understanding of the laws of gravitation, and actually taking space and time and putting them together in a coherent framework of space-time. And of course, the frontiers of science in those days really was gravitation, quantum mechanics, and we still have not yet got a fully unified theory of quantum mechanics and gravitation. So gravity operating on the largest scales in the universe, quantum mechanics governing the smallest scales in physics. And we don't yet have a complete combined unified theory of quantum gravity. And maybe our gamma ray bursts and our fast radio bursts will be the kind of phenomena that will act as beacons to help us to test new theories of quantum gravity and to help to illuminate the nature of space-time in years to come. So this is the shorthand for Einstein's equation. It's beautifully, deceptively simple. On the left-hand side, the math just codes up and tells us that space-time tells matter and light how to move. And on the right-hand side, matter and energy tell space-time how to bend, and it's that simple. But of course, it isn't that simple. What this code actually unpacks into is 10 independent, second-order, non-linear partial differential equations. And at this point, if you were all in the room, I would offer just to spend the next hour going through these equations. No, I actually really wouldn't. But what's really incredible about these equations is that there have only ever been 3 exact analytical solutions discovered. All the other solutions are numeric and have to be done in supercomputers, and they're all approximations. And those 3 exact solutions made 3 very specific experimental predictions. The first one predicted the expansion of the universe. which was subsequently confirmed by Penzias and Wilson, discovering the cosmic microwave background, so the dying embers of the Big Bang at the radio microwave frequencies. The second predicted the existence of black holes, and now you speak to any astronomer, we'll all be very happy to say, yes, of course, black holes exist really in nature. They're not just a mathematical construct languishing in the literature. And the third prediction was the existence of gravitational waves. So if you perturb space-time, you actually produce gravitational radiation. And again, discovered just a few years ago and resulted in the award of Nobel Prizes. So in fact, general relativity has been hugely successful. It's taken 100 years, really remarkable to think that we've been able to conceptualize the universe, discover the mathematics, make the predictions, invent, build, and realize the engineering and technology to make these incredible observations to test the original theories. I think as a species, if we can do that, then we can pretty much solve all of our global problems. And of course, you know, throughout my career, I've studied black holes, and you know, when we talk about black holes, we think of them in popular culture, they're in Hollywood movies. If anybody's been to see the movie Interstellar, there's lots of good physics in that movie. Don't take physicists to see that film because they'll tell you what's right and what's wrong, but it still is a great film. And I describe a black hole really as a region in space inside which nothing can escape, not even light, because the pull of gravity is so great. And we now know all sorts of flavors. We know that stellar mass black holes, which are a few times the mass of our own sun, they're a few miles across in space, and they're produced in the death throes of massive stars. When a star reaches the end of its life, blasts off its outer regions, and its core collapses to a black hole. At the other end of the extreme are supermassive black holes. They're 1 million to 1 billion times the mass of our own sun. They're about the extent of the solar system, so they're quite big things if you think about it, and they sit at the heart of large galaxies. We think they're very, very important for galaxy formation and evolution. We don't yet know which comes first. It's a chicken and egg. Does the black hole grow the galaxy? Does the galaxy seed the black hole, or is it both? We think it's probably interplay of both, and that's why we see things like quasars. We see this cosmic indigestion. When you're able to fuel a black hole supermassive, it will then produce usually radio jets, plumes of charged particles that produce radio emission. And in fact, it was radio astronomers that first discovered this phenomenon, that the jets coming from these supermassive black holes. And now we think there are medium-sized black holes. We think there's a missing link, and actually it's very difficult to know how to form black holes that are a few tens times the mass of our sun, up to 60 to 100, but we know we found them because they've merged and produced gravitational waves. So it's a really exciting time to be in astrophysics. It seems very special that all of these things are coming together, and that we seem to have an incredibly rich and coherent picture of how the cosmos behaves. And as I say, apart from gravitational waves, the only tool we have, of course, is light. Now, again, I think we live at a technologically very special time in history. First of all, we can connect on Zoom like this. That alone is special. 20 years ago, we wouldn't have been doing this. But also we have instruments that spread across the whole of the electromagnetic spectrum. So up in space, we have satellites that catch the highest energy rays from space, up in gamma rays and X-rays, which of course do not penetrate the Earth's atmosphere, fortunately, otherwise they would toast us. So for example, the Swift satellite, you'll hear more about that catches gamma ray bursts on the fly. And then of course down through X-ray and down to ultraviolet. Some ultraviolet light does penetrate the atmosphere, that's why we get sunburn, but mostly we try to use satellites above the Earth to catch the ultraviolet light, because that gives us a much clearer unabsorbed view. Visible light, of course, does reach down to the ground. That's where our eyes are most sensitive. And we've got a rich suite of ground-based and space-based telescopes to look in the visible. And then through to the infrared, again, mostly in space, and then down to the long wavelength radio waves, which are predominantly used with ground-based telescopes. But really the frontiers for me, and we've been obviously using these telescopes in different ways for many years, excuse me, is really in the time domain. And I showed you what our cave ancestors were doing in terms of time domain astrophysics. But this really is where the highest energies and the most difficult technical challenges come when we're looking at how things change on the sky. Now, if we're looking at stellar transients, so for example, a supernova remnant, we might be looking at the light coming for some of the highest energies, of course, are coming in the tera-electron volts, but we might be able to see light from these things for thousands of years. If we're looking at things like Eta Carinae, so quite unusual exploding stars, again, very high energy radiation right through to the visible light. That's a visible photograph. But you might be looking at the light from the active light from that for 100 years. If you're then looking at some of these sort of binary systems, and these accreting binaries, you might be looking at 10 days. Novae, they might be 10 days or weeks. And then when you come down to gamma ray bursts, again, very high energy, and they're gone in seconds. And so it's these explosive events in the universe, particularly the highest energy ones that may involve black hole driven processes, are the ones that I and my team are particularly interested in. But they are very technically and theoretically challenging. So that really takes me to the history of GRBs. And again, keeping in mind that you discover something and then you've got to figure out what it is and where it is. And again, that's very much still the story of fast radio bursts, for which I think we really are at the frontiers of learning what they are. So gamma ray bursts were discovered accidentally and serendipitously by military satellites in the 1960s. And these military satellites were monitoring the Earth for violations of the Nuclear Test Ban Treaty. And I'm sure for a short period of time, the scientists who discovered the first flash in the detectors may have been somewhat stressed. But it was pretty quickly realized that these flashes in the detectors were not coming from Earth, they were actually coming from the sky, they were actually cosmic in origin. And they were reported in 1973, but actually they remained mysterious. I mean, unlike quasars, active galaxies, and pulsars, which were discovered around the same time, the biggest problem was that these gamma ray detectors had very poor localization on the sky. So if any of you have optical telescopes and you're keen amateur astronomers in the visible bands, if I come and say to you, can you go and find this thing? It's gone in a few seconds, go look now. Your first thing you're going to say is, where do you want me to look? Up there is not accurate enough. And so the field really languished because we didn't have these localizations. In the early 1990s, the Compton Gamma Ray Observatory was launched. This was a gamma ray satellite which was looking across the sky. And the BATSI instrument on that, which is a gamma ray detector, started to find many more of these gamma ray flashes. And you can see in the figure there that was the 2,704 gamma ray bursts detected by the BATSI detector in its lifetime. And what was incredible is that they're uniformly distributed across the sky. There's no preferred direction to see them. Their actual 3D cosmic distance, of course, is unknown. We don't have a redshift. We don't have a measure of distance to them. We just have their projection on the sky. But they have a variety of gamma ray profiles. And you can see in the top right-hand corner what happens when a gamma ray burst flashes. Let me just go back and take you through that again. So this is a gamma ray monitor. The bright emission through the middle is gamma rays, cosmic rays being accelerated in our own Milky Way. And when you see this gamma ray burst go off, it only lasts for about 8 seconds. You'll see the trace. It brightens and it fades away. It's the single brightest thing in the sky instantaneously. It swamps the whole of the detection. Wham, just wipes everything out. So they are the instantaneously most luminous objects in the universe. But you can see from these light curves, you see brightness or intensity of the gamma rays on the vertical axis. You can see time on the horizontal axis. There's a whole different array of flash profiles. Some of them are incredibly short. You can't resolve them in the instrument on timescales shorter than 64 milliseconds. And some of them last for 10, hundreds, and we now know thousands of seconds. So there's a huge array of temporal profiles, and they're evenly distributed across the sky. So what on earth are these things? There's been many studies of their spectral properties as well, and they fall into sort of 2 categories. When we talk about hard radiation, what we actually mean is we count the number of photons coming in the higher energy band, we count the number of photons in a lower energy band, and we just do a ratio of those 2 numbers. And if something's described as hard, then it means that you've got many more high energy photons than you have lower energy photons. So it's a much more energetic process. If you've got more of a balance, or you've got more of the lower energy, and there's still high energy photons in terms of gamma rays, but they're just less energetic, then that's called a soft spectrum, and that's the pink side. So the longer duration ones seem to have lower energy photons, and the shorter duration ones, so less than 2 seconds in duration, seem to have the very hard spectrum. So they seem to be really energetic, and we had this bimodal distribution. So we didn't know, maybe 2 categories, 2 progenitors, still not knowing what these things were. And in 1995, there was a great debate. So this, I think, was the equivalent to the Shapley-Curtis debate of 1920, trying to debate, and at that point, trying to debate what these spiral nebulae were. Were they galaxies beyond our own environs, or were they something in our Milky Way? So this great debate of 1995 kind of mimicked that 1920 debate. And you can see there Lord Martin Rees in the middle. He was the chair of the debate. It was held in Washington. And you can see Bogdan Paszynski on the left-hand side, and you can see Professor Don Lamb on the right-hand side. And Don Lamb was arguing that these gamma ray bursts were evenly distributed in the sky because they were in the halo of our own Milky Way galaxy. So they were nearby, and the reason they appeared so bright in the detectors was because they were nearby, right? But like an episode of Sesame Street, near, bright, far, faint. So they had to be in our Milky Way halo. And Professor Paszynski was saying, no, I think they're cosmological. They are phenomenally intrinsically luminous, and they are at cosmological distance, and that's why they're evenly distributed on the sky. And of course, we didn't know. And at the time, if you read the literature of the time and you speak to people who were at the debate, really the people who supported the galactic origin were winning the debate. People pretty much thought they were in our own Milky Way. But what we really needed, of course, were better localizations to solve the debate. And the real breakthrough came with the launch of a new satellite. Often you have a new instrument, you make a new breakthrough. This was the Dutch-Italian satellite, Beppo-Sachs, and it was X-ray satellite. And what this satellite did, which was revolutionary, was it managed to capture the X-ray counterpart of a gamma ray burst. And what they discovered was actually, although the gamma ray flashes have gone very quickly, there is a dying ember that is left. So there was an X-ray afterglow that lasted for many, many hours. And so this satellite was able to see that X-ray counterpart. It was able to measure its position very accurately, so to a few arc seconds, and then watch how the light faded. And what this did was it allowed optical astronomers to, first of all, identify a host galaxy that might be associated, so they could take a deep photograph in the visible light that could be associated with this X-ray source. And then subsequently to actually find an optical counterpart that also came with the X-ray counterpart. Here you can see the optical afterglow of this burst that was discovered in 1997. So suddenly you have a huge breakthrough in the field. You have an optical counterpart. It was bright on the 28th of February. It faded away by the 8th of March in 1997. And the minute that you detect the optical light, you can take a spectrum. And you can take that spectrum and you can measure a redshift or an actual distance to the object, assuming that the universe is expanding. So this was hugely revolutionary, and it was immediately proven that these things were far outside of our Milky Way galaxy. They were cosmological in origin, and they are still the intrinsically most luminous objects that we've ever discovered in the universe. And our FRBs may beat us, but we'll hear about that later. Now, rapid follow-up was really important. It was important to go and look to see what was there in the position of the gamma ray burst. And as I say, rapid in 1997 was 10 hours. We now do this in seconds, but 10 hours was good. 10 hours was phoning a friend at the telescope and saying, I've got a localization. When it's dark tonight, could you take a photograph on the spectrum? Another breakthrough came in 1999, and this was incredible because this was a very, very bright optical counterpart. It wasn't superseded until a burst that happened in 2008. For those of you who are optical astronomers, the burst in 2008 was 5.8 magnitude. That's, I think, naked eye. GRB 1999-0123 was certainly binocular brightness. It was 9th magnitude. And it meant that little telescopes, little automatic telescopes or little telephoto lenses could see this. You didn't need big glass on this. And what you can see in this plot, you can see in the background, you can see the rise of the visible light up to 9th magnitude, and then it fades away. And superimposed, the spiky mini plot there is the gamma ray emission. And you can see it's just over about 80 seconds. And there are 3 points on that. They were 3 visible points. So this was the first time optical light was detected simultaneously with the actual gamma ray burst itself. So this strange disturbed host galaxy that was discovered with, this was with the GRB on and off. You can see it flashing through. Oh gosh, so my connection is unstable. And actually, because we have the distance to the object, we know how bright it is, you can actually calculate the intrinsic energy. And if that energy is put out in all directions equally, so isotropically, you have a huge energy crisis, because the rest mass equivalent energy tells us that a neutron star rest mass worth of energy was destroyed in 80 seconds, right? I mean, that's tough. That violates an awful lot of laws of physics. So there has to be some other explanation. The energy can't be put out in every direction. And what we now know, of course, is that the light is not put out isotropically. It's very heavily beamed. And so it's almost like a laser pointer rather than a light bulb. And when one of these beams points towards us at Earth, that's when we see the gamma ray flash. We now think that the explanation as to why we have the short duration ones, the short hard burst, less than 2 seconds, and the long duration softer ones, is because there are 2 different types of progenitors. So we think that the long gamma ray bursts come from the core collapse of massive stars, blast a supernova, form a black hole, shine a beam at Earth. And we think that the short duration ones come from the merger of two compact objects, so maybe a black hole and a neutron star or two neutron stars. And that actually was only really definitively proved in 2017. I'll show you that shortly. What produces the light, we think, are shock waves. So as I say, we have this beam of charged particles. This plasma is actually moving very close to the speed of light. Its bulk motion is close to the speed of light. And when it points towards us, we get an extra Doppler boost of the radiation as well. We think there's a model, it's still a model, and with the best we have at the moment, successive shock waves catch up and produce the gamma ray emission, or what we call the prompt emission. And then as that shock wave propagates out into the circumburst medium, continues to accelerate particles, and that produces the longer wavelength radiation in the afterglow that can then last for hours to days to weeks, right out into the radio waves. You can actually see these things for years in radio waves and low frequencies. And so, first of all, they're probing regions of extreme physics. You know, we're now starting to look at mergers of compact objects, birth cries of black holes. And because they are so bright, they also act as cosmic beacons. So even if you don't care about the physics of gamma ray bursts, you can actually use gamma ray bursts for cosmology. So some scientists like to use them as literally beacons at the edge of the universe, and their light comes through and shines through all of the intervening material. So you can study all of the gas along the line of sight to these bright beacons. And as I say, follow-up is really the important part. And that was really the breakthrough, the speed at which you can get on and catch that light. And as I say, a fast follow-up in 1997 was maybe half a day, and that revolutionized things. But in the early 2000s, it was realized that what we really needed to do was catch the gamma ray bursts, have a very accurate localization very early, not wait for an X-ray afterglow, and then all of our other telescopes could mobilize. And so NASA launched its Swift satellite. This was a mid-X mission, and it had the BAT is a coded mask array gamma ray detector, and that gives pretty good localizations to a few arc minutes, which is good enough for optical astronomers. There was also an X-ray telescope on there, which will give arc second angular accuracy positions, and it slews very quickly. If a gamma ray burst is detected, the instruments on board will also start to slew to the right parts of the sky. And there was also a small ultraviolet optical telescope on there, which is great for bright bursts. But of course, we've got many optical telescopes on the Earth that can also follow these up. And so this was launched in 2004, and it's been absolutely seminal ever since, and it's still working. This is a really sweet website. So you can go here and you can just see what's keeping me up at night. So this is an all sky map. In the blue are the old gamma ray bursts. In the red, it's the ones that have just gone off. You can hover your cursor over the gamma ray bursts flashing, and you start to see the information that we're all gathering, which we disseminate to our community in real time. So we're constantly updating these. And we've got some really nice databases that we're now starting to mine and do statistically. And it's a great tool for schools as well. Kids love to be able to go in and see what went bang in the middle of the night. Now, what I was doing in 2004, I just had my first son. So he was actually sleeping through the night, and I was waking up in the middle of the night chasing the birth cries of new black holes and the death throes of massive stars. And my team in Liverpool, we were there at a very fortunate time. We were building up the gamma ray burst group. And in Liverpool, we were building the world's largest fully autonomous robotic optical telescope. So these are 2-meter aperture telescopes, fully professional telescopes. We built one in Liverpool, and we shipped that to the Canary Islands and La Palma. And it's kind of badly named because really it's not in Liverpool. The sky in Liverpool is not good enough to do this, but it was built on the side of the River Mersey. There were 2 clones that were then shipped out to Hawaii and to Australia. They were funded by a businessman called Dill Folks, and he wanted schools to be able to access professional telescopes. But we also ran our gamma ray burst software on the Folks telescopes as well. So we effectively had 24/7 coverage of the night sky, certainly in the winter. And so when the Swift satellite detected a gamma ray burst, and you can receive these messages yourself onto your phones, it disseminates a signal down to ground stations, and you can draw that signal into the back of your telescope. So you get the trigger from the Swift satellite, and you can then go ahead and make some observations of that patch of the sky. So we spent a long time putting intelligence into our software because these things happen very quickly. My mobile phone buzzes and says, new gamma ray burst. I haven't got time to wake up and figure out what to do with the telescope. I certainly haven't got time to fly out to the mountaintop and think what to do with the telescope. So we worked really hard to develop quite a complex data pipeline. We catch the signal automatically. The telescope safely overrides the the observing program it's running at the time, slews to that part of the sky, starts to take measurements for us. Our pipeline would then analyze the data, figure out whether we detected a new optical counterpart, measure the properties of that optical counterpart, and then make an intelligent decision as to what the subsequent observations should be. Should we take a spectrum? Should we take more images? What colors should we take? And light curves. And it works. It would also send us a very polite little message saying, I found something, I found an optical transient. This is the position on the sky. This is its brightness, its 15th magnitude, and this is what I'm going to go ahead and do. And there's a 16-bit confidence interval that tells us how right it thinks it is. This was the very first automatic light curve that our software produced. We were a very tiny team. We'd been up many, many nights for many weeks debugging our software and wondering why things were going wrong. And would you believe it? We slept through this. We woke up in the morning and we were like, oh, did we miss a gamma ray burst last night? We didn't, because actually everything had worked beautifully. And we actually would put these automatic notifications out around the world to say, this is what we've discovered. It's quite a nerve-wracking moment when you press the button to tell 1,000 or more astronomers that you've just made a discovery. You hope you're right, and you really hope you're first. So this was the very first early time multicolor light curve afterglow of a gamma ray burst, and it started just 3 minutes after the onset of the GRB. So you can see how fast we are now compared to half a day. And we've discovered, we've actually followed up nearly over 260 gamma ray bursts since we started this. Now, as I said, we had this energy crisis. So if the light and the energy is put out in equal directions, then we're having to destroy too much mass. And we realize now that things are beamed into a jet. And that's not a crazy idea, because we know that plasma jets are ubiquitous in the universe. So whether ballistic jets like the galactic object SS433, whether supermassive black hole driven jets like the one in M87, or CFIT galaxies, which are kind of mini supermassive black hole systems and spiral galaxies, we see these plasma jets on large scales in the universe. These radio jets, actually these are radio images, are the largest continuous fluid flows in the universe. So it's not ridiculous to think that a gamma ray burst might look the same. Now, a gamma ray burst is a stellar mass system. They're at great distance, so we will never have these beautiful radio maps of gamma ray bursts. We have to infer all of the properties of the light of the plasma jets just by the time variation of the light. So we have to decode all of that. And this is what we do when we plot how the optical light fades. On the left-hand side, you can just see a bunch of multicolor light curves, and the shape of that fade tells us that we actually have a beamed source. And actually, because it's moving so fast, we only see a tiny fraction because the light is all beamed and focused into our line of sight. But as it slows down and starts to spread out, eventually we see the physical edge of the jet, and that's what makes the pace of fade change. And that's how we get the curvature in the light curve. So we know that these do have physically collimated jets, and we've seen the edges of them by inferring that from the time behavior of the light. But the real question we want to answer, of course, it's great to be first, it's great to find many, it's great to have superlatives, and it's an incredibly exciting field. But the real question we're trying to understand is what powers these things, because they're immense. And the real question that I'm always interested in, I always say to students, if you've fallen asleep in a talk and you get to the end of the talk and you think, I'm not quite sure what that talk was about, if you scratch your head and put your hand up and look intelligent, which I'm sure you all are, and say, but what about the magnetic fields? Many speakers in astrophysics will say, oh gosh, that's a really smart question, because actually you've rumbled me. I've neglected the magnetic fields because they're really complicated, but we'll hope to deal with them later. I'm sure many of your radio astronomy audiences will be thinking about magnetic fields. So maybe don't do that in a radio talk. Don't do it in one of my talks, because that's what I care about. So the big question really, when we were starting to advance our work, once we've been finding these gamma ray bursts, studying their light properties, was really what powers them, what collimates that beam, and what accelerates the plasma. And it has to be something to do with the magnetic fields. Now, we were really lucky because theoretically there were 2 competing models. One is the standard internal shock model. So synchrotron radiation is produced when an electron spirals around a magnetic field. And the original model for gamma ray bursts was that you would have these shells that would crash into one of the so-called internal shocks and produce the gamma ray radiation. And then you would have this material that would continue to go out and crash into the circumburst medium. And where the crash happens, you squish up the tangled magnetic fields that are in the circumburst medium, and you make it's almost like a thin skin of tangled spaghetti. And in those scrambled magnetic field lines, you'll accelerate the charged particles, and that produces your synchrotron radiation, which you detect as the afterglow. But this is quite an inefficient way to convert bulk movement into radiated energy. So there are some problems with that model. The alternative competing model was a thing called point-in flow, where all of the energy is in the magnetic fields. You have large-scale ordered magnetic fields that are advected out with the expanding material, very powerful acceleration, very efficient collimation. But the real problem is that they don't dissipate well, so they're not very good at radiating. So in principle, we shouldn't see them, we shouldn't detect radiation. So these were the two extremes. So the real, the real bottom line here is that the origin of magnetic fields remain unknown in the universe. We don't know the origin of cosmic magnetic fields, but it was clear that they could be very important. And we had two competing models that we could test between. Now, one of the ways to do this is to measure a special property of the light called polarization. And there had been an early claim of polarized gamma ray radiation back in 2002. And this became a very controversial result. So the RESI satellite, which is a gamma ray satellite, claimed polarized light of 70 to 80%. Now that's coherent synchrotron radiation levels. That's kind of the laser in your lab. You'll hear about, FRBs can show very high polarization. So that's the extreme. But actually those data were reanalyzed by a different team and they came up with the answer of 0. So which is it? Now, to be fair to the team, it's incredibly hard to measure polarization of gamma rays. You have to be able to calibrate your instrument very carefully. And of course, when you try to do this in the universe, you've got no other calibration source. You've just got the gamma ray burst itself. So it becomes a statistical argument. So there have been subsequent detections and the jury's still out. People are still debating how reliable these polarization measurements are, but it's very exciting so that it's still a frontier field. In the visible light, as I say, we've been studying the shape of these light curves, how the light brightens, how the light fades. But of course, we realized that what we could do, because we could get on very early, was we could actually have a stab at trying to study the polarization of the visible light. But of course, when you look at the visible light a day after the burst, you're not really measuring anything other than the tangled magnetic fields in the surrounding medium. And what we realized, the key was to get on very, very early. So as these shock waves propagate out and the forward shock sweeps out and starts to produce the dying embers, there is a point very early on where there's a reverse shock, almost like a reverberation that goes back into the oncoming flow. And the radiation from that reverse shock is the last point at which you can capture the fundamental signature of the outflowing fireball. And you have to do that quickly. Now, there are predictions as to what the intensity of the light should do, and reverse shocks should brighten very quickly and they should fade very quickly. Forward shocks brighten much more gradually and fade much more gradually. And so you have these two components, and depending on the physical properties of the medium, they will scale up and down in brightness or combine in different ways across time. So we came up with this model of sort of 3 types, where if you have a forward shock and then a reverse shock very separated, you should be able to see this in the light curve. Or maybe you have a reverse shock that dominates a little bit over the forward shock, that's a type 2. Or in a type 3, because of your magnetization properties, you're completely dominated by the forward shock. And we proved this with some of the light curves that we were studying. And what's really exciting is that the polarized, the reverse shock is predicted to be polarized, the forward shock is predicted not to be polarized. So we knew if we could get very early on, we could distinguish between a magnetized or a non-magnetized model. And we had a robotic telescope. We were getting on within 1 or 2 minutes, so we could do this. Now, we had no polarimeter. There was no polarimeter in the world that could do this because we had to do this in real time. And the way you generally measure polarization, of course, is you'll take your Polaroid, you'll make a measurement at one angle, then you'll turn it around and you'll make a measurement at another angle, and you'll measure the difference in brightness. And if you get a difference in brightness, you say, oh, I've got some polarization. But of course, we couldn't do this because our light curve's changing with time, it's fading. We don't a priori know what the visible light property is. So we had to come up with a new design. And we went to speak to Dr. Dave Clark at the University of Glasgow, and he'd invented this neat little stellar polarimeter. He hadn't had the opportunity to put it on a big telescope, but we actually copied that design and we worked with him to design this for our telescopes. And the idea was to spin a Polaroid glued to a deviating prism at about 550 revs per minute. And as the light comes down through the optics and onto the CCD, you actually encode a ring instead of a star on your CCD. Now, if the light is polarized, and you measure the light as a function of angle around that ring, you get this sinusoidal, this 2 theta sinusoid. And if you correct for instrumental depolarization, you get this nice wave. And if you fit to that, it gives you the degree of polarization. So this is a bright star, it's a 15th magnitude star, and it's 5% polarized. So this is what we did. We designed this instrument. We worked with a small engineering company in Liverpool, Precision Engineering. Couldn't do this, but then figured out how to do it, which was really exciting. Worked together, we stuck it on our telescope and we spun it. And then Easter 2006, you can see how my whole social life and my private life is governed by the dates of gamma ray bursts. This gamma ray burst went off. Our telescope slewed, we caught the light. You can see in the right-hand side, the optical light curve, it goes up, it fades up. It just looks like a forward shock. And we measured the polarization. And we didn't detect polarization. It was less than 8%. It was an incredibly powerful result. We did this 203 seconds after the burst, which was amazing. So we published this in Science magazine, and we thought that forward shocks were unpolarized. Now, when we won an award for it, and we went to a dinner. A little while later, 3 years later, we had to be patient. We caught another burst. Now, this looked more like a type 2 burst. So we had a steep fade, and then it sort of plateaued off a bit. So we caught the tail of a reverse shock for the first time, and we detected 10% polarization. That was published in Nature. And again, you can see the rings here. The other rings in the field are actually stars in the field. So unlike the gamma ray scientists, we've got all of these stars in the field that we can do a sanity check on. We measured the polarization of the stars. They were not polarized. We measured them month after month to show the instrument was stable in time. And we were able then to convince the referees at Nature that this was a robust result. So this was the very first detection of a polarized afterglow. And it showed that there were large-scale ordered magnetic fields in the fireball. So that was really important. And then, like all good scientists, we had a unification scheme. We had an unpolarized forward shock, we had a polarized reverse shock. So we've proven the model. And we then wrote various more detailed papers on the nature of the magnetic fields. But we realized the sample of 2 is probably not that great. And what we really wanted to do is grow our sample. And we also know that these light curves are incredibly variable. So on the left-hand side, what you see here in the black is a gamma ray light curve. This is quite a long gamma ray burst. It lasted for about 1200 seconds, and it's going bang, bang, bang. You can see these spikes. And it also did the same in the visible light. So this is our optical light curve. It got bright, it faded, it got brighter, it faded away. And what we were doing with the Ringo ring instrument was that we were just a single shot. We just took one measurement. And what we wanted to do is to be able to make time resolved measurements. And so at that point, EMCCDs were becoming affordable, very fast readout, no readout noise at all, so we could stack our images up to taste. And so what we did was we slowed our Polaroid down to 8 rotations per second. We took the deviating prism away. We read out our exposures at 125 milliseconds. So we had 8 exposures per second, and we had rings. I put this in because it didn't cost us very much. We recycled our old instrument. We had very little money. We didn't stick our tinfoil in the micro, but this is my favorite cartoon of all times. And this is what I threaten to my bosses: if they're going to cut my funding, I'll find a way to make a gamma ray burst and study it. So be careful of high energy scientists. And Ringo 2, it's now called Ringo still. We've stuck with that. And obviously the Liverpool connotation keeps us with Ringo. It doesn't produce rings anymore. So what we now have are straightforward optical images, point sources. We can do basic point source photometry. It's a dream to reduce. And in 2012, we actually detected this gamma ray burst, which you can see marked in the red. Very bright, and we actually just extracted the polarization for all the stars in the field, and you can see the GRB stand right above it. But what we also had, we have time sequence data, which was also really exciting. This is at a redshift of 2.2. This is a really distant source. We got onto it just 240 seconds after the burst, and we had 4,000 stars to calibrate this against. There was no doubt. We knew how to calibrate our instrument. And this was really beautiful. So this, for the first time, was time resolved polarization. So the bottom curve, you can see the light curve. It's bright, it fades, it's got a plateau. So we've actually caught, you can see in the dotted line, the 2 components. You can see we've caught the reverse shock and resolved it all. And we've got the forward shock coming up later. And we measure the polarization, which is the top curve, all the way through that reverse shock. So it was nearly 30% polarized, and the polarization just decreased with time as the full unpolarized forward shock started to dominate. And we also measured the position angle of the polarization, which was incredibly stable. It just rotated by about 15 degrees. So we've got large scale ordered magnetic fields focusing, collimating and accelerating these jets. We then built a third instrument, Ringo 3, because we wanted to do this in 3 colors, because that also gives us new information. And ultimately, we want really to be able to look at things like fast radio bursts or tidal disruption events. And we really want to start to be able to probe the nature of space-time and test some quantum gravity models. I was at a dinner, and I was telling the scientist next to me, who was a marine zoologist, that we've got this incredible camera. And he said, "Oh yeah, I know a shrimp that can do that." And I said, "I beg your pardon?" And he says, "Well, it's not just 3 colors. It's the mantis shrimp. It has eyes, or light sensitive, light adaptable eyes, and that can image in 12 colors, fast imaging, plus 4 linear and 2 circular polarizations." And I was like, oh my goodness me. that puts us to shame. I'd quite like one of those on my telescope. So if there are any optoelectronic engineers on the call tonight, please call me if you know how to do this, because these shrimp, while they have amazing eyes, are also quite ferocious. And apparently they've been known to smash through the glass of their aquarium. So they're kind of fight or food, and that's why they have such incredible eyes. But amazing. So that's really what we want to do, and to really solve the nature of the high energy universe by looking at all of these different parameters. We did a little bit of that with Ringo, and now we have an incredible picture of how these magnetic fields are driving these processes in the universe, what's happening in the interstellar medium, what's happening in the fundamental fireball physics. And we're building up these samples to try to get a much better idea about all of the populations. Back down to Earth, as an amazing team of scientists in Glasgow and internationally who have now been doing this in the lab. Serendipitously, they think they've actually caught a tiny fraction of a second of a gamma ray burst jet produced in their labs as they've been firing high power lasers at these aluminium targets. So it's really exciting now to think that we might start to be also able, just for a tiny fraction of a second, to study these in the lab. And then finally, we caught for the first time polarized optical prompt emission. So again, we were able to capture the visible light during the gamma ray emission and actually measure its polarization. And we're still actually trying to understand what that means, because the mechanism of producing those prompt gamma rays is still a matter of debate. And again, we published this in Nature. I'm sorry, I'm just going to skip this one because I don't think I have permission. And of course, you know, now moving out of the electromagnetic regime and into the gravity world, if you like. I'm not sure this is going to let me do this. Anyway, this was the very first detection of gravitational waves, and this is a simulation. You should be able to see these black holes merging. Detected by the LIGO interferometer in North America. So these are two interferometers, two very long, 4-kilometer long concrete tunnels. Light is beamed up the tunnel, bounces off a mirror, comes back. And if a gravitational wave passes through the Earth and passes through the interferometer, one arm will be slightly long, one will be slightly short, and the light will come back too early and come back too late. And you know a gravitational wave has passed through, and they're passing through us right now. I don't know if you can hear this. Or you can just let me know if you can hear this. Give me a thumbs up if you can hear it. So I hope you heard that, but that's actually the audio sound of the very first ever detected gravitational wave. These were two black holes of about 30 solar masses that each merged and were detected in 2015. There's a Nobel Prize for this. And this is the characteristic chirp just as those black holes merge. They merge and they produce ripples in space-time, and those ripples come through space-time for millions of years, came to Earth, and they were detected in the gravitational wave detectors. And this just gives me a chill up my spine. That's the sound. The dull sound was actually, the lower pitch sound was actually the frequency, and then I put it up by a little bit to actually make it a higher, more audio signal. So there are now many of these being discovered. And an incredible piece of science and engineering and technology. But a couple of years later, and this is back just to finish the story of gamma ray bursts, I said right at the beginning that one type of gamma ray burst might be the merger of a neutron star with a black hole. Now, when you have that kind of catastrophic merger, we expect those to produce gravitational waves as well. And in 2017, this very long chirp, which I won't play because this doesn't last for seconds, this does nothing for a very long time, and then it goes whoop, just at the end after about 30 seconds. A neutron star is the densest form of matter we know in the universe, a sugar cube of which would weigh the same as a medium-sized mountain on the Earth. So these are very dense things, and these are the endpoints of massive stars if they don't quite collapse to form a black hole. But of course, if you take a neutron star and you merge it with another one, it can tip it over that critical mass and produce a black hole, or it might merge with a black hole. And at the same time, the Fermi satellite detected a fairly faint flash of gamma ray. So there was a gamma ray burst almost simultaneously with the gravitational waves. Now, we've speculated about these things, but we never thought that maybe a decade before we would find one of these things together. So this was incredible. And this was really the first proof that gamma ray bursts, short gamma ray bursts, are produced by the merger of two compact objects, because we have the proof, because we detected the gravitational waves produced by that merger, which is it's such a sweet story. And the host galaxy of this burst was found. I mean, it really is a needle in a haystack job. And in fact, a spectrum was measured, and of course we have the distance to it as well. And that again is the holy grail in astronomy, is to be able to find an optical counterpart and then be actually able to measure the redshift to it. So we've got the host galaxy, we see where this thing is, and these two compact objects merged at the edge of this galaxy. And we've got a distance to it, so we have all of the energetics. This is what we think is happening. So we take these two compact objects over many millions of years, they get closer and closer, they spin together, and then eventually, all of a sudden, catastrophically, they merge and they produce gravitational waves and they produce a gamma ray burst. And when that beam points towards Earth, we see a gamma ray burst. And we also think that we make heavy metals. We think maybe half of the gold in the universe is made in this way. Also platinum. Scientists did detect a kilonova, which was the signal of these heavy metals. And so this is all of the pieces of the jigsaw came together, and it's incredibly exciting. So we're entering a new technological era. We have lots of work to do. We haven't solved everything by any means. And we're now moving into an era of really big science. So we're building new cosmic ray detectors, the Cherenkov telescope array in the top there. We have the square kilometer array, which is going to be the biggest radio interferometer ever built in South Africa and in Australia. The large synoptic survey telescope, the Rubin Observatory, is the optical sky. So this is 8.5 meter an 8 megapixel camera, so an 8 meter telescope being built in Chile, and that's literally going to do a movie of the sky. 10 years it will be surveying the sky, and that's going to revolutionize our visibility of the transient sky, millions of transients a night. We've already detected gravitational waves, and there are new gravitational wave detectors being built around the world, so we can actually get better localizations. Again, that's the big key, and we can start to probe more of that gravitational wave space. And of course, we have our high energy satellites and our global networks of robotic telescopes. So as I say, we have a revolution coming in transient astronomy. We still don't understand most of the universe. We understand about 4% of it. We have tested general relativity almost to destruction, but we like to know whether it's part of a larger, more all-encompassing theory of quantum gravity. And we still need to formulate those sorts of theories, and then we have to have some testable predictions. We're hoping we might find some new exotic particles, so the Cherenkov telescope array might help us to find things like axion-like particles. We might understand what dark matter is, and we might ultimately understand why the universe is not only expanding, but it's accelerating its expansion, which is something we don't understand. We're bound to find things that we didn't know were there, and that I'm sure will lead on to your next talk for fast radio bursts. And I think we've come quite far in our technological advancements in 15,000 years. Thank you for your time.
Yeah. Incredible, beautifully explained. That was great. Thank you so much. We've got some time for some questions before I invite Wolfgang to present. Is there anything? Ah, yes. Yeah, there are some questions in the chat.
Yeah, shall I go up?
Yeah, have a look. Yeah.
Yeah, I see one on neutrinos. Have anyone observed neutrinos been detected from GRBs yet? No, but we're looking. So we've certainly found high energy neutrinos. They're very hard to find. So the IceCube detector down in the South Pole has recently been upgraded. And it has been suggested that some neutrinos have been found from high energy jets from active galactic nuclei. So those big radio jets that I showed you, they're incredible particle accelerators. So we are really hoping that we will be able to find neutrinos from high energy gamma rays. And again, you know, as one of those parameter spaces where we're probing, that IceCube should be really important there. And again, it's matching and time matching and energy. The localizations of the neutrinos is still quite poor. So it's really a big patch of the sky. And you're trying to guess what was the cosmic accelerator that produced those neutrinos. So it's still a bit pinning the donkey on the tail rather than the other way around. But yeah, it's certainly a frontier for us. Let's see the next one. Shall I just work backwards?
Yes.
Is it possible, this is from Diane, is it possible that captured? I'm not sure if Diane would like to unmute, maybe just expand on that question. I'm not sure I quite understand the question, but maybe Diane would like to ask if she can. I don't know if she's still there. I'm curious to know, beyond in which direction? Is that beyond in spectrum or beyond in time? Maybe Diane's not there. Okay, if she is, she might be able to type in and just ask a little bit more. I had a question before I started. So AC asked me a really hard question, and I'm not sure I know the answer. Maybe I'll come back to you. How would you identify or distinguish the signal of an evaporating primordial black hole from an FGRB? Now, I think I misread that question, AC, when I first read it. I was thinking of, could an FRB be explained as a primordial black hole evaporating? And so I've answered a different question there. I mean, primordial black holes are something that we're searching for, and we think that they may grow by accretion and turn ultimately into supermassive black holes. And we're also hoping to find the first generation of stars, so-called population 3 stars. So new satellites that have been launched will help us to probe that. Certainly the supermassive black holes don't evaporate on Hubble time, so they would evaporate on longer than the timescales of the universe. And the small black holes, I think, probably you wouldn't get a signature that would be detectable on Earth. But the real question is, would a primordial black hole evaporate or would it grow? And I think we don't know. So that's a really good question, but certainly one we'll keep our eye out for. And then I'm seeing that it's just moving fast up the chat here. Said, awesome talk, thank you. Does X-ray gamma ray observations and GRBs match any cosmic ray counterparts? Yeah, again, really quite hard. So the Pierre Auger, I'll answer that in 2 ways. Pierre Auger, for the very highest energy cosmic rays, again, the localizations are quite poor, so trying to understand what the particle accelerators are that are producing those. I think that's for the next generation. We did recently discover tera electron volt radiation from 2 gamma ray bursts. So back in 2019, we had one that the precursor to the Cherenkov telescope array detected. And that was absolutely incredible. So we were very lucky. My team were actually able to get millimeter wave radio observations, and we also got visible light observations very early on, and we did polarization of that one. So that all came together really well. What we showed was that the millimeter wave, we think the first polarization measurement of a millimeter wave afterglow of a gamma ray burst. It was quite low polarized. It was just a little bit over 1%, but they were absolutely seminal observations that we made with the ALMA array down in Chile. And at the same time, our Liverpool telescope in the Canary Islands kicked into action and used Ringo 3. And again, we published that paper. And what we found actually was that the polarization was very well constrained. It was very low, it was about 2%. And we think that it was so energetic that actually the magnetic fields collapsed very early on. And so that's my PhD student, Jordan Mitchens, who published that paper, so you can have a look at that online. And we think the magnetic fields collapsed very early on as part of the shocks, and that's actually what drove the afterglow. And so again, we're starting to open up new parameter space. So I told you a very neat story about reverse and forward shocks, but now we're starting to think about that magnetic reconnection. So I think the TeV and cosmic ray GRBs, we've now had 2 of those, are really the really high energy extreme ones, and they're the ones where we're really starting to probe the magnetic reconnection model. So thank you, that's a great question. Are there any other, Paul, that I've missed, or anybody wanted to come on microphone maybe?
Yeah, we'd have some time if anybody wants to unmute and present a question.
If you were on about having a camera that images in multi-wavelengths. There's a designer that works at Durham University. He's been tinkering with crystals, where you have multiple detectors in your camera for specific wavelengths, and then you put your beam of light through crystals which take off specific wavelengths at right angles into the detectors. But it's just theoretical at the moment. He's done some tests, but he can't get the funding to build the camera.
That's really interesting. So we looked at this early on for the Ringo design. So we looked at some calcite crystals. There is one polarimeter that works that way. First of all, the purity of the crystals has to be very, very high. Otherwise, you induce polarization and you can't calibrate it. I have started a project with a different colleague at Durham, actually, to start to use some of the quantum detectors in the hope that we'll be able to just photon count. So my real passion, I think, would be to capture every photon from the sky, tag it in energy, tag it in polarization, tag it in position, and then just shove it in a computer and do a big data science crunch on it, just number crunch, cross-correlate it with gamma, with gravitational waves, and say, there you go, that's your entire universe parameterized. So that's my life goal, and also to solve the mysteries of quantum gravity. But, you know, just a couple of things to do on a weekend. But thank you for that suggestion. If you've got a name and you can share it offline, that would be really great, and I'll look into it.
I can tell you his name. It's Jürgen Schmoll.
Oh, lovely. I'll look him up then and have a chat. Thank you so much for that suggestion. Really appreciate it.
Any more questions for Carole before we move on? If we were in real space tonight, I think you'd get a standing ovation, Carole. That was just fantastic. I can see that we'll have to get you back again in a couple of years to see how far you've got with your life, with your life's ambition.
Absolutely. And you can invite me back in the future and I'll tell you what we're doing in the radio, because we have some radio predictions and we'll be able to tell you, well, predictions for the square kilometre array. And hopefully whoever makes the observations, whether it's my team or somebody else, they'll be able to prove us right or wrong. But yeah, it's been a real pleasure to speak to you, and thanks for your applause and your questions. Thank you.
In July, we do have Prof Madsen joining us to talk about his work with neutrino detection at the Ice Cube.
I'll listen in then. Yeah, stick me on your mailing list. I'd love to
I can do that, yes.
Thank you.
Yeah, thank you. Thanks again, Carole. Right, I'd like to invite Wolfgang to join us from Stockholm, Australia. I know Wolfgang was having comms problems earlier in the evening. Are you on the call successfully?
Yes, I'm there.
Oh, perfect.
After 2 restarts of the computer, somehow it worked. Okay, so shall I start?
Please continue. Yes, yes, yes.
Okay, so that should be full screen now, I hope.
Yeah, that's fine.
Okay, so let's move from the high end of the electromagnetic spectrum down a bit on the wavelength to the radio. And what I would like to do is give you an update on the results of fast radio burst observations. That's taking up the story from, I believe, was last May, when I reported on our first observations, for successful observation of fast radio burst. And just let me explain what has been happening since. Just a few words on this FRB that we are observing. It's one of those repeating fast radio bursts, so it's not observed only a single time, but multiple times. You may recall that it's at the moment debated whether all fast radio bursts somehow repeat or not. That's certainly still an open question. Now, this particular fast radio burst was first detected in November 2020 by the CHIME FRB collaboration, so the big telescope in Canada. And it has a dispersion measure of around 413 parsec per cubic centimeter. Because it's a repeating fast radio burst, it has been possible to determine the host galaxy by radio interferometry. And this radio galaxy has a redshift of 0.098. So the distance is roughly expressed in light travel time 1.2 something billion years. So it's a sort of a moderate cosmological distance, not that far away, but still a cosmological distance. Now, in May last year, I have shown these 2 observations. They were brand new off the press at the time. These are very bright events. Just remind you that we have a 25-meter telescope, so it's limited in sensitivity. And these are very high signal-to-noise ratio events, even for our telescope. During this observation period, that was actually triggered by the report that this fast radio burst had shown several pulses within a short period of time, meaning within a couple of days. So we continued observations, and during this period, which went all the way through May, we had 2 more events that were detectable by our telescope. So these are weaker, but still fairly clear detections. this was something extraordinary for us. Of course, fast radio bursts are well known, but for us running a moderate telescope as amateurs, it was quite something to have FRBs to be observed. The one that we observed was exceptionally bright, that had a peak flux density of more than 400 Jansky and a fluence of 1200 Jansky milliseconds. So this is probably one of the brightest fast radio bursts ever observed. It doesn't mean it's the most energetic because it's fairly close. It's sort of, if you look at the total energy that's released, is sort of in the typical range of fast radio bursts, but it's a very bright event. We did, during this time, we did a lot of exchange about the results with other telescopes. And this is a sort of a summary. There are a couple of other telescopes of our size. There's Westerbork, one of the Westerbork instruments, which is also a 25-meter instrument. Then there's the Onsala, the Swedish telescope, also a 25-meter instrument. And then there's a 34-meter in Poland. And what I have shown here is each of these vertical lines show when an observation has been done. So there have been numerous observations. Some of them were overlapping, and they were also done in different frequency bands. So Westerbork most of the time was in P band. Onsala, like ourselves, we did it in L band, and Toon sort of mostly did it in C band. And the result of the observations are shown here. This is, again, is from the time period of April, late March, April last year. These are the 4 Stockard detections, and there are more detections by others, and some were simultaneous observations. So we had one event which was simultaneously detected at the Onsala telescope and ourselves. The other instrument had to pause their observations due to some other commitments in the EVN network. So that's why there's a gap. But as you can see, we continued observation and there was nothing more to be seen. So it was clear that sort of the activity phase was over. And at some point in time, we stopped the observations, or only did it occasionally to see if anything was going on. So we had essentially an activity phase of this fast radio burst last year, starting end of March timeframe and going into the May timeframe, and then it was silent again. Now, what we did in late last year and this year was to upgrade our instrument. Essentially, the main change was that we have now new and better low noise amplifiers. These are extremely low noise because they are room temperature, still room temperature, and they're extremely low noise for a room temperature device. And we did some more technical things like moving the location of the IF down conversion from a prime focus to a more easily accessible place. And then we had a trouble with our calibration noise source. The main thing was really the change of the LNA, because that gave us a dramatic decrease in system temperature. So the system temperature dropped from 90 Kelvin to 35 Kelvin. Again, this is with a room temperature receiver. And accordingly, the system equivalent flux density went from about 1000 Jansky to 380 Jansky. The system equivalent flux density is a good measure for the sensitivity of a radio telescope. It tells you how bright does a source have to be in order to create the same signal as your background noise. So essentially it's a 3 dB increase of your signal, and that really improved well. This upgrade was completed in early February, and we already knew while we were still working on the instrument that this FRB had gone into a new activity phase, because we heard from our friends at the Onsala telescope and others that they have seen bursts again. So we were really eager to get it going. And as soon as we had things up and running again, we started observing. That was on the 9th. And immediately, that was just within a few hours after we put our instruments back on, we had 2 fast radio bursts on the same day. So we were very happy about that. So we just turned it on, the instrument, and immediately had 2 fast radio bursts. This was for us the trigger of a intensive observation period where we essentially had daily observations. This source is above the horizon for about 12 hours on our side. So we used most of that time to do observations. And it really was confirmed that we have a high activity phase. So these are the next 4 that we had. And it continued another 4. This one, I'll come back to that later. This is fairly weak, but I'll come back to that and explain why we are certain that this is a fast radio burst. Maybe it's interesting to know that the morphology of the pulse can change quite a bit. So it's a triple pulse here, and some are broader, some are more narrow. Then we have further observations where again we see a different structure, where in this case, as you can see here, the events is spread out over some period of time. So there are multiple events within a time frame of tens of milliseconds. And this again was seen here, where we have spread out. And it continued on and on and on. This one is a more bright, wider example. This is fairly bright. And maybe I should explain a bit why you see a structure over the frequency. So this is the frequency here and the time. And you see in all these events that the intensity varies over frequency. And this is scintillation, a well-known effect that we also know from pulsars, that the diffraction along the line of sight, this has nothing to do with the atmosphere, like in optical. It's just the fluctuations of the interstellar and intergalactic medium. And I go back to see this scintillation behavior everywhere. Okay, going back to that. And these are the last ones that we had observed. And the last one, again, spread out over some 40 milliseconds. This was on the 22nd of March. And ever since then, it's now the 1st of April, we haven't seen anything. So again, we have seen a activity phase of this FRB, which is now probably over. So we have to be patient to get something running again. We are at the moment, we're still continuing our observations, but it seems that we really have reached the end of this activity period. Now, activity periods for FRBs is something that's, I would say, quite typical. It's observed in other FRBs as well, that they have periods of activity and then the activity goes down. And there are at least some where this activity period is periodic. So it comes and goes at regular intervals. We don't know whether that's the case for this FRB as well. We have seen it last year in the May timeframe, April timeframe, and now we're in February, March. And so we have to see whether in X months from now, we again have an activity period, or whether that's something different. Of course, the reason why why these activity periods are there and why they eventually are periodic, that's still up to speculation, as is the source or the source of the FRBs in general. It may be interesting to note or compare notes again with other instruments. there's this one pulse which Omar from Astron called the Trident of Poseidon, this triple pulse. And this is our observation, and this is a simultaneous observation by the Westerbork telescope. They have a wider bandwidth than we, but what I did is I cut it out and sort of aligned it with our observation, and one can see that the scintillation pattern matches. So it's, as one would expect, that the scintillation is identical between the two telescopes. They're not that far away. Another interesting comparison might be this one. That's a comparison with Effelsberg. We had a joint observation with Effelsberg. And on that particular day, we said, well, we haven't seen anything. And they said, well, we have quite a nice event, which we have captured. And we asked, well, when exactly was that? And then we looked back in our own data at exactly the same time, a fairly weak signal, still recognizable, but it's weak. And we simply, our detection threshold was not low enough to capture that, but it's a simultaneous observation. But it shows one thing, that if you look at FRBs with a 25-meter instrument, you're looking at the tip of the iceberg. The majority of the FRBs are much weaker than you can detect with a 25-meter instrument. And that's clear that we look at the very bright end of these events. The others remain hidden to us. This is very much underlined by an observation which was done by the FAST telescope, the 500-meter telescope in China. They had a, if I recall correctly, a 25-hour accumulated observation period of this FRB, and they said they detected something like 3,000 pulses in that time. And we detect one every day or so. And it's the same object, and but it's really a big difference in collecting area that makes a difference. And you can imagine if you go to the square kilometer array one day, how much and how many FRBs you will be able to detect. But still, for us as an amateur group with for an amateur quite a big instrument, but for the professionals a smaller instrument, that's at least something that gives us much joy. Okay, thanks very much, and I'm ready to take questions.
Thanks, Wolfgang. I was interested to see that the morphology of the pulses can be quite different. Is there any comment as to the mechanisms that would create the different profiles?
Well, since we since we don't know what exactly is the mechanisms that creates fast radio bursts in the first place,
yeah, sure.
We don't know. But there's one thing which is really striking for us. Where one of the other subjects that we are doing is magnetar observations. We're monitoring one magnetar, which became radio bright by the end of 2018. We are monitoring this ever since then. It also comes and goes. It has a period when it's brighter, and it has periods when it's less bright. And this magnetar also has periods when it emits very strong single pulses, meaning they are so strong that we clearly detect them as single pulses with about the same or sometimes even higher signal to noise ratio as these one. If you put these side by side and also look at the variability of the morphology of these pulses, you can tell one from the other. You see exactly the same pattern. You see single pulses, you see some which are broader than this. You see multiple structure, and you also see, let me go back to that one. You also see in this magnetar effects like that, where you see multiple pulses spread out over, in the case of the magnetar, sometimes 200 milliseconds. So Of course, there is speculation and some background why the repeating fast radio burst could be magnetars. There's still a gap in energy, of course. The brightest magnetar that has fired in our galaxy, in the Megayansky range, still is not as bright as a distant fast radio burst. But I find it very striking that if I take the pulses, put them side by side, and from the morphology, you can tell whether it's a magnetar in the fast radio burst. Scientifically, that doesn't mean anything, of course. There has to be much more behind it, but it's certainly a trigger and worthwhile looking into that in more detail. Having said that, there's one effect that is known. I'm not sure whether I find a good example here. Not really. There's an effect which is known as Satron bone effect. That is when you have an FRB with multiple pulses or a structured pulse, there's a tendency that the pulses or the part of the pulse that arrives earlier has more energy in the higher frequency and sort of goes down in frequency. And that's why it's called a Satron bone, because if you translate into audio, it would be wah, wah, wah. We haven't seen a Satron bone on the magnetar yet. I mean, we have something like over these years, 60,000 events from the magnetar, which are detectable as single pulses, and we haven't seen a Satron bone there. So that's sort of a counterexample. Anyway, that's something that we spent quite some time on, looking at the magnetar, looking at the FRB, and see whether we can find something that supports the idea that FRBs are magnetars. But at the moment, the only thing we can say, they look exactly the same, but they are, of course, at completely different distances, and therefore at completely different energy levels.
Yeah, thanks, Wolfgang. Just a couple of questions in the chat. AC is asking, the scintillation spectra seems to be conserved in time. Over what length of time would it be expected to remain stable? Also, have any of your observations been correlated with time?
So the first question, typically the scintillation variations, if we talk about the effect of the scintillation that comes from our own galaxy, from the Milky Way, we are talking in the minutes to 10 minutes range when the scintillation pattern changes. That's when we look at pulsars, for example, the scintillation pattern changes in that time scale. However, this is also has something to do with the motion of the pulsar. So if you have a pulsar that's actually moving away from you faster than another one, the scintillation pattern gets shorter. At least that's the idea. For the FRBs, one has to consider that also the host galaxy may be contributing to the scintillation, and also the intergalactic medium. So I don't have a conclusive answer to that. I would guess that the scintillation fluctuation timescales are similar as with pulsars. None of these observations have been simultaneously with chime. I'm not sure how much overlap we actually have with them time-wise. They're 9 hours is the time difference. And we have 12 hours of observation time, so there may be some overlap, but we haven't checked with them what has been observed simultaneously. Another aspect is that's also maybe kind of interesting. Chime is observing in the 400 to 800 megahertz range. That's pretty much where Westerbork has been observing in the past, and you can see there has been no detections in the P band. They observe somewhere around 350 megahertz, and it seems that the activity or the energy in L band seems to be higher than in the lower frequency range.
Yeah. Sajid is asking, can you tell us what LNA you're using with the very impressive noise temperature you've got now?
Yeah, that's an interesting story. These LNAs are a donation from Caltech. There's a gentleman at Caltech. His name is Sander Weinreb, and he is a specialist in LNA development. And these LNAs, they are based on a indium phosphide PHEMT transistor, which is made by a Swiss company. And Sander has taken these transistors and created a very good low noise amplifier from that. And we have also been comparing our receiver now with, for example, with Onsala, and we have the same system temperature, but Onsala has a cryo LNA, so that's a cooled LNA that they have, and we achieve the same number with the room temperature. It's a very impressive piece of equipment, and we're so happy that we got those donated. And that was a very generous move from Sander Weinreb. I'm very grateful for that. It's not commercially available, so.
Alan Kennedy is asking, do any of the FRBs have an optical component associated with them?
To the best of my knowledge, no FRB has ever been observed optically.
And finally, from Carole Mundell, are they synchrotrons self-absorbed at lower frequency, or is the lack of emission at P band intrinsic?
I'm afraid I don't have the answer. Sorry.
Great. Yeah, thank you. Thanks very much, Wolfgang, for sharing with us tonight. And I'm sure as the story of FRBs unfolds, we'll have you back again to update us.
Yes, well, as soon as we have the next activity period, I'm hoping to show you some more of these events.
We look forward to it. Oh, and another question coming in from AC. Any observations in S-band?
I think there have been observations. Well, in general, yes, there have been observations of FRBs in S-band. And for this one particular, I think Effelsberg had observations in S-band.
Right. Thank you very much. Yeah, round of applause from everybody here for you, Wolfgang.
Thanks very much.
And finally, but last but not least, all the way from Alaska, I would like to invite Whit to share some very recent observations of our very active sun. So much closer to home now. Can you stop sharing, Wolfgang?
Yes, I'm just trying to find the right button to do that. There it is. Okay.
Okay. Hey, thanks a lot for that, Wolfgang. That was really interesting. Let's see. Let me share my screen. I know everybody's anxious to go have a whiskey or something, so I'll try to keep this as short as I can.
I just got to fill my glass up.
There we go. I'm seeing full screen. Is everybody else seeing that?
Yeah, that's good.
Okay, I just want to quickly show some solar radio observations that came in recently from the HARP facility, about 300 kilometers from Anchorage, where I live. And these measurements or observations are at a much longer wavelength than what we've been previously talking about. So we're in the 10-meter range right now. And this first one here, it came in on the 30th of March, 1730 UTC. And this is a type 2 solar radio burst that shows harmonics and band splitting. And what's really interesting about this, if you can see my mouse, we see the fundamental burst right here. It's a type 2, so it's a slow sweep, sweeps from high frequencies to low. And you can see that we have the fundamental down here. We have band splitting here. We have the second harmonic here, and what looks like a third harmonic up here. So this is the first type 2 solar that I've captured with any of my systems where I've actually seen the third harmonic in it. So this is kind of unusual for me. And besides being really pretty, this is quite interesting type spectrogram. And down here in the lower area, you see below 20 megahertz, from 10 to 20 megahertz, you're seeing a lot of regular broadcast and ham radio and other activity that shows up in my spectrograms every day. So that's a nice type 2 that has harmonics and band splitting. This one is another type 2 with a type 4 noise storm that followed it. And the type 2 is very weak. You can see it over here just to the left of middle. And it only covers maybe from 35 to 50 plus megahertz or so. And then the noise storm follows it over here on the right-hand side. And there's also some additional activity over here. So that was captured on the 31st of March, just a couple days ago. And now this one here, you're going to have to look at very, very closely because it's really hard to see. This was about a half an hour after the previous slide, and it shows gravity waves. And if you look really closely, you'll see slightly lighter blue areas that curve up from the lower left to the upper right, and they're in bands. And Christian Monstein, who's the principal investigator for eCallisto, actually pointed these out to me. He called them Caustics gravity waves. And now I don't know a lot about optics, but Caustics is a word from optics, and I believe it has to do with lensing and focusing and things like that. So we probably had something going on in the ionosphere that caused these gravity waves in the high frequency band. So if you look real closely, you can see the bands sweeping up from the lower left to the upper right. So those are the three observations that I've got. And just a little bit about the instrumentation. There's the antenna at the HARP facility that I installed last year. And it's buried in snow, but it still works. In fact, I've had people that saw this picture ask me, does it work like that? And I guess so, because some X-class and M-class solar flares, which are extremely strong and moderately strong, certainly are being received by that guy. So this picture here was just taken a couple days ago, about the time these bursts were being captured. So it's still winter up there. And in fact, I think it was 8 degrees Fahrenheit there this morning when I checked. Here's the instrumentation, the receivers that I have. And these are I mounted them in a portable cabinet like musical band members use. And you can see the two Callistos, one for each polarization of the LWA antenna over here on the left. Those are the Callistos. In the middle here, you see the LWA Power Coupler, which is my own design. And that couples the power out to the antenna. And it also has a quadrature coupler built in so that I can derive circular polarizations from the two linear dipoles. And then over here on the right is a dual up converter. So this gets me from 10 megahertz up to 80, maybe 85 megahertz RF, and then outputs at 200 megahertz that goes into the Callisto. The native range of the Callisto instruments is 45 to 870 megahertz. So the up converter gets us down into the lower frequencies where the where we see a lot of activity coming from the sun. So that's pretty much all I've got. I just wanted to share that quickly with you, and if there are any questions, I'll be glad to take them.
Those are the best radio spectra I think I've ever seen from a Callisto. They look great.
Yeah, they're beautiful.
So you're bringing the lower frequencies up so that you can actually measure them in the receiver. That's understandable. But I thought that was kind of polluted by all that other broadcast frequency stuff going on.
You mean the 10 to 20 megahertz?
Yes, that's right.
Yeah, those, and the only reason I'm going down to 10 megahertz is I just want to see where the cutoff is for the ionosphere. Typically, it's in the neighborhood of 15 megahertz. And I'm trying to find for the HARP facility if that holds true there, or if it's higher or lower or whatever. So yes, you're right that there's interference there. But if I have a burst coming in from the sun through the ionosphere, at some point it's going to get cut off. And I'm hoping to catch that with that lower frequency.
Do you ever get to see some data peeking through the noise otherwise?
So far, no. I haven't been running that the system at HARP that long. It's only been there for less than a year at where I'm set up right now with the LWA. So I've got a ways to go with that.
And this is only with one antenna right there that we saw in the picture.
Yeah, it's a cross dipole antenna, so it's just a single antenna.
Thank you, Whit. Very good.
Yeah, thank you.
It was interesting that you picked up gravity waves in the ionosphere, because in the optical you get gravity waves there with the noctilucent cloud. So I wonder whether the two are related.
I don't know that much about gravity waves. In fact, I probably would not have recognized them in that spectra unless Christian had actually pointed it out to me. So I've got a little bit to learn about that.
Why all the 50 ohm terminations?
Say that again, Paul.
AC is asking in the chat, why all the 50 ohm terminations?
Oh, yeah, let me go back to that, and hopefully I can explain that. Over here on the right-hand side, you see two splitters, and these are 1, 2, 3, 4, 5, 6 port splitters. And so this way I can hook up multiple receivers to the single antenna. And each one of the ports that aren't being used at the time are terminated with 50 ohm terminations up here. So that's just good RF practice to keep reflections and make sure everything is terminated properly.
So you're not cutting up the frequency spectrum. It's just multiples, different taps.
Yeah, it's essentially, yeah, different taps.
Thanks, Whit. Are there any more questions before we conclude our evening? I'll take that as a no. To our speakers tonight, I just thank you so much. What an interesting, well explained, and stimulating evening. Thank you so much. And we will see you again next month. If anybody's at the BAA Winchester meeting, do drop by and say hello. Anyway, until next time, good night, one and all. Good night.
Okay, thank you. Good night.
Right.
Thanks. Good night.